Okay, so today, April 2nd, we are going to finish talking about exceptions today, and basically that is everything you need for the final exam, everything up to exceptions. It's a slightly different order than listed here, so um, yeah, but basically after exceptions, we're going to take, we'll have a little bit of time left, so we're going to do a couple things that are extra to the course. One is passing functions as parameters and lambda functions and things like that. It'll be quite short. And the other is performance, also pretty short. Um, and then whatever happens on Monday, we're going to do a review of the practice final. So the practice final has been released. I may update it a little bit, but I think the information that is there is a very good guide as to how to study. But we'll go over some specifics on Monday, and we'll drop a few hints about stuff that's going to be on it. Probably a short class on Monday. So if you're making a special trip in, I don't know, you can always just watch the video, but also, happy to have you, of course, if you're on campus. Tutorial 10 technically due this weekend, but all tutorials have been extended to 8 a.m. on Thursday. A.m., right? There's always at least one person that emails me to say that they read it as PM or something. But so please get those in on time. And your test 2, I was looking, it's not quite marked. If it's not marked, I will mark it myself tomorrow. There's only a few left. So yeah, you'll have your grades by tomorrow at the latest. But that's where we stand. Any questions? Okay, so we're going to finish talking about exceptions. Last class, we did the barnyard harmony. We had seen how, the big general theme of exceptions is how it messes with the control flow of our program and the consequences of that. So in terms of how it messes with the control flow, well, we had a for loop. The first case, we had the for loop inside the try catch, which means that if some error is thrown in one iteration of my for loop, it abandons the for loop entirely. And that might be what we want, but then we tried this other approach where we put the try catch completely inside the for loop. Then the error is handled inside the for loop, and the for loop will continue after that. All right, so that's just not super groundbreaking anything, but things you have to watch for when you're using exceptions. All right, so then yeah, so then so far we've been using single catch statements, or catch blocks, but we can actually have a try with multiple catch blocks. And the compiler is going to do a little bit of work and find the first matching catch block, or the first catch block with a matching parameter to what was thrown. And so this can have certain consequences, especially when we're using subclasses, derived classes, which we often would with an exception. So, oh, sorry, wrong one. So here we have our good old, our good old barnyard. These are now just empty classes, but the same hierarchy is in effect. We have animal as the base class. We have bird that is a descendant of animal, and a chicken that is a child of bird. Cat is a child of animal, etc. That means there is a relationship between these different animals, like chicken is a bird, is an animal. And then we're going to declare a chicken, a cat, and a pig. And then we're going to ask the user for some input. And then based on whatever the user inputs, we're going to throw a bunch of stuff. So here we're throwing a bird. we are statically allocating a temporary bird object and throwing it all in one go. But down here, we're throwing a chicken that we made before, and here we're throwing a cat that we made before, and here we're throwing a pig that we made before. And if the user enters something we don't recognize, then we just say whatever. Okay, so sec. So because of that is a relationship, well, what's going to happen? We have the try block, and inside the try block, a bunch of stuff might happen. A bunch of different things might be thrown. And then, well, what the compiler is going to do is as soon as something is thrown, of course, it's going to look in the current function for a catch block. It's going to find it. It's going to find multiple. So it's going to start at the beginning and say, well, is the thing thrown? Is it a chicken? And if so, we're going to jump in here. And then next, it's going to look here and say, well, if it wasn't a chicken, then is it a bird? And if that is true, then we're going to, execute this. But whatever happens, we only execute one catch block. and then we pick up down here. What is going on? Down here. Okay. So, all right, select your activity. So if we throw a pig, we get a pig alert. Nice. If we throw a cat, we get a cat alert. If we throw a chicken alert, and a bird, we get a bird alert. So everything seems to be working correctly. And if we throw something that's not recognized, like an animal, we get this caught something. So here we have the catch-all. The last catch block has the catch-all if everything else up to this point didn't catch whatever was thrown. All right, so seems rather straightforward. There are some things to watch out for. So there is a little note here saying that order matters. And so if I do something like this, what are the consequences of this? Anyone want to take a guess? I put bird before chicken. Right, well, let's try it out. First of all, let's compile. And well, right away, the compiler recognizes something's not right. Exception of type chicken will be caught by an earlier handler, specifically bird. This is one of those, this is a rare instance where the compiler tells you exactly what's wrong and it's absolutely correct. This is almost never happens in C++. So yes, our chicken, if we throw a chicken, well, the compiler is going to come here and say, is a chicken a bird? And the answer is yes. And so it will get caught here. But I just get a warning, actually. I can still run this. Select my activity. So if I say bird, it says bird alert. That's great. If I say chicken, I also get bird alert. So not so great. So the catch block for chicken will never get used because of the specific order that I put these in. And so, well, based on that, maybe we can try a little experiment. What happens if we put the catch-all first? Well, the compiler is handler is masked by default handler. So it'll let you get away with a little bit, but if I try to do the catch-all first, it says, listen, you're getting carried away. And if I try to compile it, of course, I get a straight out error instead of just a warning. So the compiler will put up with a little bit, but not too much. All right, there's something else here. Well, I think that's about it. So the rule is that if I have a multiple catch blocks that are catching objects that are in a class hierarchy, then I should, for instance, if I ignore aircraft and boat for now, let's look at vehicle, car, and Mazda. Well, what should come first is the the most specialized class, the lowest derived class, let's say. So Mazda should come first, and then followed by car, and then followed by vehicle, which, well, that's not what we did here, actually. Actually, we did something wrong. We put the vehicle first, which means that whatever I throw is going to get caught in this first catch block. So actually, if I took that away and then, put vehicle here, imagine that said vehicle, then the order that I have these catch blocks in is fine. Right, so questions on that? So this question appears on every single final exam in this class, always, without fail. So just know how this works, right? I ask you a few questions on exceptions, and this is always one of them. Because it's easy. It tests your understanding. And yeah. So if you only study a few things about exceptions, you should study that thing. All right. So, well, that brings us to rethrown exceptions. So in addition to multiple catch blocks within the same try, we can actually have multiple try catch blocks sort of, what's the word? We can have a try block within a try block, right? And then what that means is that, well, if a exception is thrown and then caught, well, we can handle it. And then maybe we can't handle everything. Maybe we just got some stuff we want to handle in our function. And then before our stack frame is popped off, we handle that, and then we throw the error again, rethrow the error. So okay, so here we have an example we've seen before with when we have this little throw parameter. Well, should we talk? What does check name do? Check name definitely throws an error. All right, let's just come back to that a little later. Okay, no, that's not what I want. Sorry. Oh, all right, settle down. Okay, so we'll come back to that throw parameter. For now, this is just the same example we've seen before with Timmy. There we go. All right, so we ask for a name. This enter name might generate an error. Specifically, if I enter Timmy, I'm going to throw this. And well, it's going to pop this off the stack frame as it's looking for a catch block. So we throw it here. There's no catch block. So we pop that function off the function call stack. We look in here. There's no catch block. We pop that function off the function call stack, and then we land here. So let's do that. And then mess with it. So enter a name. If I enter my name, everything is fine. If I enter Timmy, Timmy's been kidnapped by a giant squid and abracadabra. Well, we've talked about that before. So let's see something different now. Maybe in my enter name, I know that this might, throw an error. And I don't necessarily want to handle the error, but maybe I have some stuff, I have some cleanup I want to do. Right, so I can do something like this. I can say, well, if any error is thrown, please come and stop here on your way back to the original try catch. Error cleanup. At which point I'm going to say, well, I know that there's more to do, so I'm just going to rethrow whatever landed here. So in this case, there's actually no parameter, or this is a catch anything. So I do not have a specific variable name. So I'm just gonna write throw, and that will throw whatever. So if I say Timmy now, then I get this handling my own error cleanup, and then I still land back in the main function where the error is printed off, and then I print out the name abracadabra. So the control flow is still the same, except I make a pit stop here on the way back to the main function. And if I did something different, like, well, maybe I knew what was coming. So, well, in this case, I could also throw, I mean, I can specifically throw the error, right? That's nothing wrong with that. So I've caught this error, and then I've done something with it, or maybe not. Maybe I just wrote something out, and then I can rethrow that same error. Or I can say, well, maybe I'll handle this error, but because of this error, I know something else has gone wrong. So I can say like new error from what is this? Enter name. So I can catch this and then just rethrow another one. And then, so handling my own cleanup, help, Timmy's been kidnapped by a giant squid. And in the main function, we say new error from enter name. And yeah, so yeah. Rethrowing the error questions. Okay. Well, that brings us to really the whole point of this whole thing. Oh yeah, this throw clause. Let's take a look at that. So what if I bring this back? And so this states that this check name function is not allowed to throw anything. And in fact, if I do throw something, this is just going to crash. So if I make on this, I get a warning. Throw will always call terminate, right? But it's just a warning. I can still run this code. And then Timmy, and then well, as soon as I try and throw Timmy, this program crashes. Okay, so just a little thing. There is extra stuff written here that I could specify some types, but this has all been deprecated. Right, so as of the current version of C++, you can't do this. You can only declare that you will throw nothing. Not in this case, I would say the older versions of C++, you could say, well, I'm throwing either an int or an exception, but if I throw anything else, then please crash. But yeah, that no longer works. Okay, so that brings us to stack unwinding. Stack unwinding is, well, I mean, basically, if we just boil it down, it's what happens if we have a delete line that is never called in our code because I threw an exception. So delete or close a file or save a file or whatever. So there might be some unfinished business somewhere down the call stack, but we're going to worry just about this call to new here. So this piece of code, we initialize a variable on the heap. Then we read in a bunch of elements into that variable. And then as long as the person wrote, they entered digits and not any characters, then we will bypass this. If they enter a character, we're going to throw an exception. But assuming everything went well, we're just going to print out everything that they wrote and then delete that array. So let's see what that looks like when we run it. We get a warning. I'll fix that later. Okay, so ARR1, number of elements. Let's say I want to enter 3 elements, and then 1, 2, and 3. It says you entered 1, 2, 3. Okay. And if I say 3 elements and I say 1, 2, and B, well, then I have a bad input error. And well, as a consequence, actually, if I run that with valgrind, And 3 elements and A, B, and C. I got a bad input and I definitely lost some memory, right? Because this piece of code never gets run. Okay. In fact, all of this doesn't get run if I throw an error. So before we get started on the solution, well, let's think about this solution. Why don't I just do this? My array 2 size. So what have I done here? I've statically allocated an array. And so let's take a look at what happens. And why that might be dangerous. So I have my main function, and then I call initialize. So main goes on the function call stack, and then initialize goes on the function call stack. We'll just shorten it. And then I'm making a pointer to an int array, and then I'm declaring a new array, and that's going on the heap. And that's where my memory leak is occurring. So what I decided to do instead is to statically allocate an array. So what happens is that, well, I can do that. Even though I've already made my stack frame and I know, it's sort of a fixed size, but I can add to the top of it. There's nothing on top, so I can say, well, I can make an array of ints on top of that stack frame. And now it's statically allocated. And if we pop off that top stack frame, then this gets deleted automatically. Seems like a decent solution. So let's take a look at what would happen if we try to use that. So I'm not going to do anything with it, but I am going to allocate I'm going to make a statically allocated array. Number of elements, 1, 2, 3, and then 1, 2, and 3. Works great. So what's the problem? Problem is this. What if I enter like a billion? Well, this might take a while. I'm not exactly sure what it's doing right now, other than maybe trying to allocate more stack space or something. What's that? Oh yeah. Yeah, it crashed. That's to be expected. It's just a question of how long it takes. So what did we do? We used up all of our stack and crashed. Task manager. You think of a jump in RAM, maybe? They're already just sucking up all the RAM. I'm not sure. Yeah. All right. It doesn't show up here, but yeah, it was a fun idea. All right. So we can't do that. But if I take this away, and 6, 7, 8, 9. Oh, whoops, I forgot to recompile it. Sorry. Control C. Or I guess we'll wait. Wait a sec. Hilarious that doesn't work. All right, so here, 1, 2, 3, 4, 5, 6, 7, 8, 9. On the heap, no problem whatsoever. Okay, so that's why. So if I'm not sure, right, what size this array is going to be, it's a lot safer to put it on the heap. All right. So just putting it on the stack doesn't help. So I need my dynamic memory here. And what are some solutions? Well, one, I can, this is This is actually a terrible solution. I don't even know why. I think I want to get rid of it at some point. But let's say I wanted to do something like this. So I have some dynamic memory. Well, first of all, I wouldn't even do this. If this was my problem, before I throw it, I'm just going to delete this memory. But let's say that this happens somewhere up the function call stack. Actually, none of this makes sense, but all right. Next semester, I'm taking this example out. But let's say I attach this to my error, and then I throw my error, and then up here, the catch block, I handle this memory. Okay, so that's, I think it's sort of even pointless to do. See, got to run that with Valgrind. Three and A, B, and C. And yeah, we get some, it's not exactly happy with us, but we don't have any memory leaks. So that's a start. I'm not sure what I did here. All right. It might be complaining that well, I don't know what it's complaining about. Okay, so that's one option. That's not a great option. First of all, there, I mean, just off the top of my head, I can think of at least one better way to do this. But even if I did do this, then, well, I have a piece of code here. Now, let's say I add more dynamic memory to this function. First of all, I have to change this function. I have to change this class as well to handle it. I have a lot of changes in a lot of different places that are linked, and that's usually a sign of a bad design. So terrible idea. Let's try idea number two, which is a little bit better. Here, we're going to do things a little bit differently. We're going to go into this enter int function, and this will just read in an element. And so for each individual element, I'm going to check to see if this flag has been flipped or not. Okay, and then let's run that. So the number of elements, 3, and A, B, and C, and that's bad input. And I don't even have to check. I know that's a memory leak because this would not get run. None of this was output. So what I'm going to do is, let's do this. It doesn't actually matter if the try block contains the for loop or the for loop contains the try block. But we can catch things and then catch and release, right? So I want to clean up after myself. So I'm going to delete this my array. And then I'm just going to throw the error. So I know that something might potentially be thrown from this function. So I'm going to wrap it in a try catch. And then in my catch block, I'm going to handle all my cleanup, right? Delete this, maybe close a file, maybe save some state, whatever I have to do. And then rethrow the error to be handled up the chain of command. So now 3 and A, B, and C. Oh, I did lose. What the heck? That is interesting. Oh, I guess maybe I didn't recompile. 3, A, B, and C. Error bad input. Oh, yeah. Let's run it with Valgrind. Okay, so I just didn't recompile it. So yeah, now that memory is handled. And this is good. This is a good design, or at least a much better design, right? So this function If I make changes to this function up here, I can also add a change here in the catch block, right? So if I add more dynamic memory, I can just delete it. And I'm not violating encapsulation. Nobody who calls this function needs to know how I do my business, like how I clean up after myself. All right, question. Okay, the last one, which is sort of the, I guess, the best one, let's say, or at least the one that works the best. And that is this resource acquisition is initialization idea. The other name for it is, or the other way to describe it is to say that if I have dynamic memory, I tie it to a piece of static memory that I know will automatically get deleted no matter what. Right? So if I statically allocate this int array object, well, whether I get to the end of this function and then return, in that case, the destructor is called, or if this throws an error and the stack frame is popped off, well, I still get my destructor called, right? So the destructor gets called no matter what. So the destructor is the finally, from Java of the try catch in C++. It gets called no matter what. So, all right, so what is this int array class? Well, I can just make a light wrapper for my raw array. Raw arrays are notoriously dangerous anyway, so I'm going to just wrap it in a class. Here I will say array equals new int and of size. And then if of course, if I say new in the constructor, there's a good chance I want to call delete in the destructor. All right, so now this is responsible for itself. And then the last thing is, well, I just want this to be I want it to be an array, basically. I want it to still work the same as it worked before. And so I'm going to overload this so that I don't even have to change any of my code. I'm actually not going to even do a bounds check here. I'm just going to say, well, in the documentation, I'll say, be careful, because if you access bad memory, that's on you. And so, yeah, all I need to do is return by reference this this integer, and then I can print out a value, and if I happen to throw an error, this will get destroyed for me. And it uses dynamic memory, so all the big chunk of memory is on the heap, and on the stack is just this little tiny class. And then, so the number of elements is 3. I can say 1, 2, 3, works fine. 3, A, B, C, throws an error as it should. Val grind. 3, A, B, and C. Bad input, but no memory leaks, and not even any warnings or stuff like that. All right, so that's really the 3 ways to handle stack unwinding in a more or less graceful manner, with the last one being, I guess, the most graceful. Okay, so yeah, this goes through. This is terrible. Put all pointers in the catch parameter. I mean, I wouldn't even do that. I don't know. I'm going to take it out for next semester. It's a bad example. Put a catch function in every called function that might potentially need it. This is a better idea. The best idea is just, well, I'm just going to attach it to an object, right? Smart pointer would work as well, but of course, smart pointer does not work with an array, at least not the way we wrote it, right? Because we have a special delete call for an array. So what we wrote is essentially the smart pointer of arrays. All right. And then, yeah, well, if you want to be reminded of what those things look like, there you go. And when I was preparing today, I completely forgot about GDB, but no big deal. If anyone's interested, we can go over some of this stuff on Monday. I will tell you a few basic things about GDB to use it. GDB is a debugger, and well, the way I show it is from the command line. And so if you use if you use Visual Studio, you can set it up so that it runs for you, and it's really a nicer experience, right? I don't have to remember all the commands. I have a readout of all the variables, and I see which piece of code I'm at. However, like everything, it's helpful to understand how these things actually work. So let's say that I wanted to use GDB on my program, and so this is from an old assignment. But in the assignment, we have a driver class, and of course, like all the classes in our assignment, we compile them into object files. And if I just do it the regular way, and then well, this is 12,336 bytes, which is fine. But I won't be able to use this with GDB. Right? GDB needs extra information. What it's going to do is it's going to tie the machine language to your actual code. And so you'll be able to step through your program and see which line you're executing. So to get all that extra information, we add the -G flag when we compile our object files. And when we link everything together, I'm not sure if that's absolutely necessary for the linking stage, but I'm pretty sure it doesn't hurt. So if we add -G, we can see that, well, we went from 12,000 bytes to 114,000 bytes. So it got a lot bigger, but it's just, there's a lot more information. So you wouldn't release this, but this normally, but I can also run it with GDB. The other thing is the assembly code that it produces is slightly different, right? So when you compile normally, it might do some optimization, but when you're trying to debug, that can be confusing because, I wrote this and this is what I get. So it compiles non-optimized assembly code. So it's not even as good as it would be, but still good for examining the logic. And then what you're going to do is, if this was called 4, you would run GDB A4, and you would get something that looks like this, right? So this is with the, I believe this is using the GDB layout next. And what it does is it gives you some views into your code. So the first one you get might be the, well, this is the assembly code, right? So this is what we're compiled into. And so you can examine that if you want. You can see what assembly code is being generated, and that might be useful, becoming less and less useful. You can also, if you look at the next view, well, then I get, this is my code, and along with my assembly code. So I can see exactly where in the real code and in the, well, not the real code, but the C++ code, and where in the assembly code I am at the same time as I run through my program. Or probably what you'd be most interested in is just the C++ code. And then from there, there's some commands where you can put in breakpoints. So you start running. I start running and I say, put a breakpoint at line 5, and it'll stop there. And then I will be able to see all the variables that have been created so far, right? There are commands for that. I don't remember them off the top of my head. If you have a good IDE, then it's all integrated, and it'll have a readout of all your variables. It's kind of cool for, I mean, this is for heavyweight problem solving. Like print statements for the size of the programs we write in this class. I find print statements I like them. They're lightweight, right? I don't have to do all this, right? I just print, and then I have pretty good intuition about where the error might be. But if I'm having trouble tracking it down, well, I can go to the extra work to compile all this and then fire up GDB and walk through it. Yeah. So yeah, it's pretty fun. I don't know, you should try it at least once just to see what it gives you. Again, though, if you integrate it with Visual Studio, it's a lot better. But questions? Okay, I'm not going to go over all of that. Again, if anybody wants to see it on Monday, we can take a look. Okay, so that is it for the course, basically. This stuff technically does not, well, this is an elaboration of stuff we've already seen in the algorithms in the STL. So, you know, there might be there won't be any deep questions on it on the final, but there, you know, there could be like, hey, pass in a compare function to a sorting. But yeah, so this will be short. Function types and variables. So how do we represent a function type? And how do we store it in a variable, right? It's just a pointer, as it turns out. Each function is just a memory address. How do we pass these functions as parameters and or using variables? How do we use lambdas? And finally, something we've already seen, but we're going to see where it fits in the context of all this using classes to represent functions. So C++, strongly typed language, and that also applies to functions. So if I use a variable, that variable must have a very specific type. And once I declare that variable, I can't change the type, right? So that helps. It seems like a pain, but it's very useful for debugging. Sometimes I read Python code and I'm just like, I don't understand what, it's like, you have parameters and they're just variable names. There's no types. So this will just work with whatever. And it's like, wow, I don't know. Maybe sometimes you just get used to a certain type of thinking, and maybe that's all it is, but I have trouble with that. So in C++, functions can also be variables. We can have pointers, references, and these variables must be strongly typed as well. So we've talked about a function signature, which is different from its type. So a signature is, of course, the name of the function, the types of the parameters, and the orders, excluding the return value. So the compiler says, well, if I call foo and I pass 3, then the compiler looks for a function called foo that takes a single int or has some default parameters and doesn't care about the return type. Return type is immaterial for calling it. But for a parameter or a variable that holds a function, we need the return type. So we need all the parameters, the type and the order, and the return value, and that uniquely defines our variable type. All right, so let's take a look at the first example. So simple, we have an add function that takes 2 integers. We have a multiply function that takes 2 integers, and we have a subtract, and they all return ints as well. And so yeah, we're just going to do some yeah, and forgot to make the make files, so we'll do this the old-fashioned way. Enter 2 integers, 4 and 5. Should I add them, multiply, or subtract? I am going to add them, and I get 4 plus 5 equals 9. Okay, well, let's say that we want to do something similar to this, but we're going to write the code that we want. So or operations. Result is, and then instead of add, I mean, I could put add, but I want a variable called func, and that's gonna work for this. And then in here, I would say, func equals add. And then here I put func equals multiply, right? And these are just memory locations of where the code is being stored. And then func equals subtract. So I want a variable that this will work for, essentially, right? So let's write it. Let's write this variable. Well, it has to return an int, right? Because here I want to print out an int. So we'll put int. It's called func. Takes two ints as parameters. That's looking pretty good, except, well, the compiler says, thinks that I'm forward referencing a function, right? I can tell by the syntax highlighting that it's yellow, that the compiler thinks this is a function. So I have to tell it it's a pointer to a function. So I might be tempted to do this, which that's a good first step. But now the compiler thinks this is the function that returns an int pointer. So I have to give it even more hints. I have to say, no, this is a function pointer. So that's it. Oh, look at that. All the errors went away. So this is a very kind of old school way to do it. I think this, pretty sure this works in C. I would have to look that up, but I feel like it would work in C. Whoops. Enter two integers, 4 and 5. Addition, multiplication, subtraction. Let's try multiply. The result is 20. And so, yeah, I was able to store this basically address to these functions inside this variable and then call it later on. Okay, and that is the most primitive way to do it. We're going to look at two or three more ways to do it. Questions? Okay. Well, that's just as a variable. We want to also use it as a parameter. So let's actually just write a function called invoke. It takes x and y, and then a function. And well, I know how to write it now. It looks like this. And then inside invoke, I just want to put this code. Okay, so what are the ways to call invoke? Well, I can say invoke x, y, add. And then invoke x, y, multiply, and subtract. Okay, and then so these can get passed, and I mean, this is just a variable, right? That's just a pointer to a function, and I'm pointing to add, multiply, or subtract. And so 4 and 5, if I subtract them, I get -1. Okay. We're going to write a different invoke, and we're going to do some fancy stuff here. Not too fancy, but this is actually kind of ugly. And one of the things that can happen is, well, what if my function takes a function as a parameter, right? So the fact that the variable name is in the middle is sort of not great, right? Because now I can have, well, instead of this being an int, this can be a second function that maybe returns an int. You could say func2. And then, well, I can also take a function, right? But something like this. And now this is starting to get really confusing. And one of the things that, well, Go, if you're familiar with Go, the language Go, Golang, they address this, right? So they have sort of a weird way of writing parameters. I forget exactly how it works, but so they saw this problem and they headed it off at the pass. Well, so did C++. We have this functional library, and this functional library allows us to sort of write this a little better. I'm going to put the function type. It is a template, returns an int, two int parameters, and we'll call that func. Which is nicer, because if I have these nested, functions in here, it's starting to be more clear, right? So I have type followed by the name of the variable. So it's going to look a little bit better. I think Go actually reverses it. They put like the name followed by the type or something. They do something weird, but when you have all these nested functions, it actually works a lot better. So let's try invoke 2. And invoke 2. 2 integers, 5, 7, and let's multiply them, and we get 35. So that works okay. All right, so a little bit cleaner syntax. Questions? All right, finally, let's make invoke 3. And how are we going to do that? Well, we are developers. Let's put our lazy hats on, right? This is all way too much work for me. I just want to do this. I just want to say, well, that's some type, you figure it out, right? I'm going to pass you the function and then make the compiler do the work to figure it out. And so I'm just going to make this a template. All right, so now if I call invoke 3, well, what does the compiler do? When I compile it, it takes this and substitutes the type for T. And it does it without me having to do anything. And then it tries to compile it. And if it compiles, then it says, great, well, here you go. Here's a function for you. So not only will this work for this case, but this will also work for like kind of related cases as well, if we want. Whoops. Nope. There it is. The 2 integers, 3 and 4, and add them together, and the result is 7. Okay. So this is 3 ways that we can pass functions into, or we can write a function that takes a function as a parameter. Questions? Okay. So, well, that's great. So these are the 3 ways. You declare the type directly. We're going to see that this kind of has some weaknesses as we use lambdas. Use a template and let the compiler do the work. Wonderful. Using the functional library, also good. So in some languages, functions are what's called first-class citizens. So these languages are Haskell. If you take 3007, you might use Haskell, or you might use, what is it called? Lisp. It's Lisp. It's a Lisp dialect, whatever it is. I forget. These have functions as first-class citizens. So now you can write these fun, fancy functional programs. In C++, we don't quite have all of that. So to be a first-class citizen, I have to be able to assign a function to a value. Yes, we have that. Pass it as a parameter. Yes, we have that. Construct expressions. So I want to combine 2 functions and get a new function. We don't necessarily have that, although I'm pretty sure you can get it. I'm pretty sure there's ways around it. But really, it's not natural for the language. So in Haskell, for example, you can compose functions. I could say G and X, put them together and evaluate something that looks like this. But we do have lambdas. So lambdas are anonymous functions. And well, that has a lot of, I mean, there's a lot of ways to write anonymous functions, but we have anonymous functions, plus we can capture some of the surrounding environment. So here we have invoke 2 with our function. And here we can see that I took away the pointer. So when I use it as a parameter, the compiler is a little flexible on syntax, which is kind of weird for the C++ compiler, but there you have it. I think you can actually also do this if you like. The compiler doesn't care. It still works exactly the same. But so we have invoke 2. We have invoke 3, which I've changed a little bit. We'll get to it later. We have invoke 4, which is a template, but also X and Y are types. So this is really flexible, right? I mean, there's all kinds of stuff I can do with that. But it will definitely work for this. All right, so I want to call invoke I'm going to skip the operations part. I'm just going to say invoke. I'm going to pass in X and Y. And now I need to pass in a function, and I'm going to use a lambda to do that. So the first part, capture clause. Second part is parameter list. Now, I'm going to write this. I'm going to name them because I'm going to write the code as well. The return type, trailing return type. So we have this weird syntax. This is not necessary. We'll talk about that in a second. And then the code. So open brace, close brace. Let's end that. And so, yeah, we have an anonymous function. And, well, if we're going to add, let's return X plus Y. So this should add my, my numbers X and Y now. Two integers, 4 and 6, and the result is 10. So our little lambda, we sent it up to this invoke 1, and it was accepted, right? The type matched, and then it ran. So let's try it with invoke 2. See if functional will accept a lambda. And 6 and 7, the result is 13. So invoke 2 also works. We'll try invoke 4, templated version. Uh, 7 and 8, and the result is 15. Okay, so they all work with lambdas. Well, I mean, maybe we spoke too soon. So the other thing the lambdas can do, well, a couple things. First of all, this not necessary, right? So if I want, I can leave that off, and the compiler will infer the return type by whatever I happen to return. So P3, 4 and 8, and the result is 12. So I don't have to be explicit about the return type. The other thing is this capture clause. So let's say I declared a third int w that is a local variable, and I want to use this local variable in the function. I want to say, well, that kind of makes sense. I'm declaring this function in this context. Why can't I use one of these variables? And I just have to declare that I want to capture it. So I'm going to say, well, please capture W. And now I still have a lambda. The lambda the type is slightly different though. Now this cannot be converted to a regular function. This is a lambda function. So yeah, my argument types are int, and the lambda. So my old-fashioned invoke using this function declaration doesn't work anymore. Not for these new and improved lambdas. So let's try that with invoke 2 with the functional library here. And well, the problems went away. Enter two integers, 6 and 7. The result is 23. So 6 plus 7 is 13. And then I added W, which is 10, which gave me 23. So this functional, not only does it solve a syntax sort of problem, but also it's better in that it accepts lambdas that use their capture clause. Okay, let's try invoke 4. Where we just infer the type. And, well, no errors so far. 90 and 90. And we get 180 plus another 10. We get 190. So the compiler is perfectly happy to infer that type for us as well. Just the one thing we can't do is convert it to a regular old function. It's a new and improved type. All right, questions? Okay. So in Voc 3, I did something. So because here I'm actually passing this by value. And I can instead pass this by reference. And well, 90 and 90, and I still get 190. So what's the difference? Well, the difference is, I mean, somebody else can change the value of this, right? So this still points to this local variable. And so if I look at invoke 3, I've changed it slightly to actually also accept this third parameter and pass it by reference. So I'm going to change it. So I'm going to pass in invoke 3. Now I'm going to pass in W and also capture it here. What is your problem? All right. So I'm going to pass in W and also capture it. And I'm going to, let's change this actually. I just want to see W's value. So W is, all right. We're getting deep in the weeds here, right? So if this starts to become confusing, I mean, don't worry too much. This is just what do we mean by pass by reference? It's that I could actually change the value of this W from somewhere else, and I'm going to change it right here. And then when I call func, that change will be reflected. So 2 integers, doesn't matter. I'm not doing anything anymore. So W is initially 10. I change it to 3 here, and then I say W is 3, and then I call func, which had captured W, and it output W is 3. When I pass by reference, if I capture by value, then it retains its old value. So if I pass by reference, then somebody else can actually change the value of my captured variable. If I pass by value, that's not the case. Yeah, questions? No, stuff I just I guess I kind of nerd out about this stuff sometimes. I'm like, oh, cool, I wonder if you could do this. And also, what happens? I captured this, I capture it by reference. What happens if I return this lambda and then pop that stack frame off? I'll be honest, I'm not sure. I don't know if that would be an error, right? Because now I'm referencing a variable that's gone, that's deleted. Maybe the compiler would catch it, I'm not sure. Haven't actually tried it yet. All right. So the last thing we're going to look at, well, let's talk about lambdas a little bit. So the syntax, they always start with this capture clause with the square brackets. It can be empty. Then we have the parameter list. We have an optional return type, and then we have the body where we put the code. Additionally, we can say that it's mutable or not mutable, or we can say some exceptions are thrown. Not going to look at those things. Also, we can capture the surrounding context and pass it by value or pass it by reference. Right, so here we've captured W and Z by reference, or we can say, I'll capture everything in the surrounding context by value. So whatever variables I have access to in my current function where I created this, I want you to make copies of them in my lambda. Or pass them all by reference, right? So just give me, I'm going to make changes maybe perhaps in this thing, and you're going to, the value of your variable will reflect that. All right, and you can mix and match. I could say, give me everything by value except for W passed by reference, or give me everything by reference except for W, pass that by value. All right. The last example is functors, technically. I don't know if that's widely used, but that's sometimes used. We've seen examples of this before, actually. We're going to make a class that behaves like a function. And then we're just going to see which one of these it works with. Right, so which invoke. So I'm going to use a struct. What do I have to do? Type def, right? Type def struct. I'm just being lazy. I don't want to type public and then indent. This is called mock. And I'm going to, I want to return an int operator. Parentheses, and I'm taking two ints x and y, and return. We'll just do an adder, x plus y. And I believe this is going to complain unless I make this const. All right, and again, we've seen this before. We did one in our I'm actually doing this back. I think I can just do this. I think I could just say struct my adder. I don't have to. This is C. This will still work, but yeah, we've seen this before when we looked at the standard template library. So now I'm going to make a version of my adder, and then I'm going to try and use it to add stuff up. So if I try it with the regular invoke, well, that is the old-fashioned way here, and that doesn't work, right? So this is very, very limiting in terms of what we can pass if we declare a function like that. Although sometimes maybe that's what you want. So invoke doesn't work. Invoke2 uses the functional library. And invoke2 is fine if I use a struct instead of a function. Well, let's make 100% sure. The two integers, 4 and 5, and I want to add them together, and that will use my adder, and the result is 9. So that works for invoke2. Invoke3 is we infer the type by using a template. And no errors. Of course, T is going to compile, right, if we use a class. 4 and 7 in addition, the result is 11. Okay, so that was, again, we've seen that before, but just to show you, if I'm going to pass one of these, functors around, how do I do it? Well, I can do it with a template. I can do it with the function library, but I can't do this, unfortunately. All right, questions? I can also do it explicitly, right? I can say my adder. Yeah. Yep. Yeah, so this is one of those things. For this, nothing. For declaring templates, if there is some difference, it's buried deep somewhere in Stack Overflow. I've not come across it. I've looked. So as far as I can tell, these have the same function here. Type name can be used, of course. We've seen it before to give compiler hints on templates to say like this is a variable, this is a type. But yeah, that's also a use that I don't really, it's like I have a very tenuous grasp of like why why we need to do that. But yeah. Yeah. Does that answer your question? Other questions? Okay. All right, so that's, I believe, the end of that. The end is correct. Yeah, so a little short one. for the last 10 minutes, I guess we'll talk a little bit about performance. I don't want to talk for 10 minutes straight. So I'll talk a little bit and then I'll jump into an example that hopefully, you know what? Let's do the example first, I guess. Well, let's talk a little bit and then do the example. So we're going to look at why should we care about performance. We're going to look at the CPU architecture and what that implies about performance, like how we can get the best performance out of our code. We'll talk a little bit about assembly, not really. We'll talk about object-oriented programming and its weaknesses when it comes to performance, right? So a lot of times, that's one of the things I don't like about object-oriented programming is it hides. It just says, no, this works all by magic. The price is zero. Well, the price is never zero, right? Even things like dynamic binding, like polymorphism, there's an overhead to that. It slows down your code. And then we'll look at data-oriented design, which is not like data-oriented design is not replacing object-oriented programming, at least not anytime soon. Neither are entity component systems, but this entity component systems and data-oriented design are used in Unity. They have a library that works. It's called the DOTS, I believe, which is data-oriented something. So there is actually an instance of this, and if you learn how to use it, apparently it gives you good performance on your games, right? Because Unity is it's a bit slower than Unreal, right? They make it easier, but that also slows it down. Generally speaking, of course. So yeah. Yeah, why care about performance? So software engineering is about trading performance for abstraction, right? So Python is nice and very easy to use, but awfully slow. C++ is kind of the opposite end of the spectrum. It's a race car. It's hard to build. You need special tools to maintain it. It breaks down a lot, but goes very, very fast. So there's room for both of these languages, of course. So why care about performance? Well, it doesn't matter until it does. It doesn't matter basically until you're successful, and then it matters a lot, right? So games, of course, it always matters. Real-time system always matters. But also, if you make an app and 100 people use it, great. Whatever code you write, it's going to work fine. If 1 million people start using it, all of a sudden, you need to pay attention to performance, right? Now it has to work. And there are stories, I didn't link them today because I knew I'd be kind of rushed through this, but of places like Facebook and Twitter or X or whatever, having to rewrite entire systems because they reached a scale where the old system no longer performed, right? So performance doesn't matter unless you're successful, and then it's going to matter a lot. And in fact, Facebook, so what happens is they didn't write the whole system from scratch. Facebook was built using PHP, which is this ancient scripting language for HTML. And they got really successful really fast, and PHP is not really made for that. And so instead of rewriting their entire code base, they rewrote PHP to make it faster, right? They have an ongoing, they have people that are working on this language to improve it all the time. So yeah, it does work. It does matter at scale. Also, energy consumption, right? If we care about the environment, then how much, whether you have an n-squared algorithm or a linear algorithm, that's going to matter a lot. Yeah, so here are some stats. Yeah, I don't think, unfortunately, I don't think we're going to get to the example today. But yeah, so this is a little dated because it's 2025. I think I looked up, I was going to replace these, but then well, I got busy with other stuff. But I think I looked it up, and I think it's around 3%. Like this was a pretty accurate prediction. By 2040, they expect maybe 14%. And I mean, AI is like really sort of, people are just making server farms so they can make large language models and then whatever. I don't know. We'll see if that keeps going. 10 planned server farms in Israel. This again, this might be a little dated, but it's the equivalent to 250,000 households or another 170,000 cars. I mean, that's a lot. That's a significant impact on the environment. So how do we manage this? Well, I mean, you kind of have to drill down to the hardware because the hardware is what's actually doing the work. And that's what's actually impacting the environment. And so when we are writing code, we have to drill through these abstraction layers to figure out what's actually happening. And that's difficult with languages like Python and Java. Right? We'd have to look at the Java virtual machine or the Python interpreter. C and C++ are a lot closer to the metal. All right, so Moore's law you've probably heard about. And it still seems to be going, right? But it's sort of leveled off in terms of CPU performance, single core performance, basically, because of the thermal limits. So essentially, all electrical signals travel at the speed of light. So if I have a CPU and I manage to cut the size in half, or I guess it would be a quarter of the area, well, it'll go twice as fast, right? If I have the same number of transistors and same architecture, because they travel at the speed of light, but half the distance is twice as fast. So the size and distance matters a lot in terms of speed. So we're reaching thermal limits in terms of how small we can make CPUs, but the GPUs, then where we just pack a bunch of transistors and do a single instruction, multiple data, those are still going strong. But all that's to say that while CPUs, we've sort of reached the limit to how small we can make them. I mean, they're still coming up with new tricks, but it's not increasing as fast as it used to. Well, the speed has gone way, way up, but the price of like going to RAM still stays the same, right? So if you look at, I mean, they can't really pack the RAM too close to the CPU because everything needs to be cooled. And you don't want to pack these things on top of each other where they're going to compound their heat. So yeah, so we get something that looks like this. We get a CPU with a control unit. I mean, one of the things I would like to bring back is a bit of a hardware or computer architecture course where we learn about how this works, because you'd be surprised at how simple this is. Like a CPU is not complicated. Making a fast CPU is very complicated. But making a CPU that does everything a fast CPU can do, but much, much slower, is kind of easy. It's not that hard. But what we do to make it fast is we put some memory right on the chip. And so if I want to add up two numbers, I load one number here and one number here, and then I add them together and I store the number here, for example. And then I write it back out to the memory. Well, that's what really costs, is this access to memory. So in order to help, we pack as much memory as close to the CPU as possible, and we do it in layers and levels. We have our registers, which are the closest. We have an L1 cache, which is small but close, and then we have an L2 cache, which is a bit bigger. And we have an L3 cache. If we have a multi-core processor, then this will be shared. And then we have RAM. And so the big problem, the big limiting factor to how fast our CPUs can go, because they will eat up data as fast as we can send it to them. But if I have to get my data from the L1 cache, well, that's going to cost me 4 cycles, right? So the CPU is going to process 4 instructions while it's waiting for its data. If I have to go to the L2 cache, that's 10 cycles. If I have to go to the L3 cache, that's 40 cycles. And that means that probably my CPU is going to be empty. Like if I have to go to L3 or to RAM to get data, my CPU is going to be sitting there empty of instructions and empty of data, just waiting for me to get it, which is why we have all these cache layers, right? So what happens is, if I have to go to RAM, right? If I have my vector here of values and I have to go to RAM and say I want this value, well, we're going to take this and we're going to copy all that into L3. And then we're going to take this and we're going to copy all that into L2. And then we're going to take this and put that in L1. because what happens is that if I want this value here, well, the next value I want is probably here. And so as long as it's still in the L1 cache, it's going to be very, very fast. I'll be able to get instructions and data to my CPU quickly. And so next class, we will finish this. It won't take very long, but I will demonstrate that this is indeed true. I will show you some tools in Valgrind for profiling it. None of this is on the final, so don't worry about it. And then we will take up the practice exam, and I'll give you some hints. And so yeah, that's it for today. I have office hours tomorrow if anybody has any trouble with tutorials. Yeah, and that's it. I'll have a good weekend. I'll see you next week.